Hello everyone, and welcome to the third video for this mini course. So today, as I mentioned last time, the goal of today is to prove the correspondence between extremal metrics for Laplace eigenvalues, harmonic maps, and minimal surfaces. So I should say that like videos 3 and 4, they are completely independent, and they are just they elaborate on some points in the first two lectures, right? So if you're just interested in district correspondence part, you can safely skip this video, just take it for granted, and go on, just go straight there. Okay, so let me first remind you what you're going to do. So the first step in that correspondence was the extremal matrix in the conformal class. Right, so the first step what we discussed is that this theorem of Joshua, Sophie, and Elias that tells you essentially that if you have an extremal metric in the conformal class for the kth eigenvalue, then you have a map to a sphere by kth eigenfunctions. So right, so this was the first step. Then I told you that such maps are automatically harmonic. And that's going to be our first goal, right? So our first goal is to prove this theorem and to establish that such phi has to be harmonic. So let's go on with it. And I want to make some remarks first before the pass to proving. So something which is called conformal covariance of Laplacian in dimension 2, right? So recall we have a Riemannian surface and Laplace operator on this G on the Riemannian surface. And we talked about the conformal class, right? So conformal class of metrics is just a collection of all metrics which are conformal to the background metric, right? So what you take some fixed metric G, and you consider all metrics which are positive function times this metric. So they form conformal class. And it turns out that one of the reasons why Laplacian on surfaces is of particular interest is that you have this conformal covariance property, right? So this is only true for surfaces. It's not true for higher dimensions. So what happens is that if you consider Laplacian of function in the metric of the same conformal class, then the only thing that happens is that the inverse of this function pops out in front, right? So this is, again, so this is just direct computation, right? So I gave you the formula at the beginning of the very first lecture. You can use the formula delta D as well if you want, but this is direct calculation. And you'll see that for dimension not equal to 2, there's going to be an additional term in here. But for n equals 2, it disappears. So you're going to be using this throughout today. All right. So what is the extremal metric? Right, so let's now go into this. So we want to prove this result, right? So what does it mean to be extremal, right? So extremal by definition just means it's a zero of the derivative, right? So whatever derivative means, right? So it's locally extremal to the first order, right? So you want to show that it's kind of a maximum to the first order. So let's first answer the question: how do you differentiate eigenvalues in general? Right, so it's a question interesting even for family of operators on finite dimensional space, right? Even that question is even there, it's not trivial, right? So how do you differentiate eigenvalues if you have a family of operators, right? So for that, let's just look at the following setup. Suppose we have some family of metrics, GT, Laplacian this metric I'm going to just denote by delta T, just to save time. And I'm going to be using dot notations, right? So D dot for me, so something dot, for example, Laplacian dot is d dt at t equals 0 for Laplacian t, right? So in general, dot, I'm going to be just using dot to denote anything g with respect to t at 0. Okay, so we have family of metrics, we have Laplacian. And now suppose that we have even more, right? So suppose we just have the family of eigenfunctions. Right, so we have this Laplacian t of t equals lambda t of t. Right. So in general, this needs proving, right, that you have this family which depends differentiably on t, for example, right? Because now we're going to take derivative of this. So in general, it's proving, but it can be done, right? In some sense, it can be done. It can be shown that there exists a family. If you perturb your magic a little bit, there is a perturbation of the eigenfunctions, which such that it's C1, right? So you can, it's not C1, but it's at least Lipschitz, right? So you can still find the derivative at almost every t, which is good enough for our purposes. So what we're going to do, let's take a derivative of this. Just dot derivative of this equality, and it's just this, right? So you take d dt, and then you plug t equals 0. Right, and very naively, like I'm not trying to do anything profound here, right? So just using Leibniz rule on the left-hand side and the right-hand side. So I have this equality, right? So this one is this. You could try to extract lambda dot from this. However, there's one very annoying part, is that it depends on f dot, right? And in general, finding, you can prove the existence of this ft, but actually finding this ft explicitly is hard. You don't actually hope. There's no real hope to be able to compute f dot explicitly, right? So you would like a formula which does not depend on f dot, right? So formula for lambda dot, which only in terms of f. And somehow miraculously here you can actually do that. So what you can do, you can multiply this. So you can take scalar product of this in L2 with the f itself, right? So let's do it. Or in general with any lambda eigenfunction, right? So let's, for example, take f. So you have this equality. And something interesting happens is that you look at this operator, this term over here. Laplacian is self-adjoint operator. So you can take this and move it over here, right? So it's self-adjoint, symmetric. So you can move it inside the L2 product, and then you do that, you get Laplacian f. But Laplacian f is lambda f, right? So you get here you get f dot Laplacian f, but Laplacian f itself is lambda f. So those two terms are actually the same. These two terms are the same, and so they cancel out, right? So those cancel out. And you can rearrange the terms, right? So f dot terms cancel out, and you get the formula for derivative of the derivative of eigenvalue just in terms of the eigenfunctions and delta, derivative of delta, right? And this is remarkable. This is what allows you to actually do anything in this area. It does not depend on f dot. Right, so the question that remains is that what happens with this delta dot, right? But that's actually easy, right? So if we're considering, so for now we're considering extremal mixing conformal class. So let's take a deformation inside conformal class, right? So we take this deformation of the initial metric G by this such that omega 0, right? So omega 0 is just 1. Right, so we take a deformation of the initial metric so that and compute the derivative with respect to this parameter t. Right, so then what do you have? So now a Laplacian t, as we just discussed, right? It's just e to the minus omega t pulled out in front, and this is just usual Laplacian of metric g, which doesn't change. So when you differentiate this, the only thing that differentiates is this part, and since omega 0. Sorry, I did say omega 0 equals 1, right? I did. This is not what I wanted to say. I wanted to say it's equals 0. Right, so I wanted this to be just a deformation of the yes, so I want that G0 is just G, right? So G0 is G. All right, so therefore, when I take t equals 0, right, the e to omega t becomes 1, but I still have omega dot in front. All right, so this is my derivative of Laplacian. And now let's go back to the formula for lambda dot and put everything back in. right? So if I put everything back in, one thing to keep in mind, right? So this omega could be anything, omega t could be anything, but we do require that area is preserved. Right, so why do we do that? Because we otherwise, so our function is not actually just eigenvalue, right? It's eigenvalue times the area. And here it's just easier to assume that the area is fixed on the deformation and differentiate only the eigenvalue, right? So you'll get the same result if you assume area changes and you differentiate using Leibniz rule, but that's just a bit longer. Computation is a bit longer. So we assume that the area is fixed, and this imposes condition on omega t, which is the following, which is this, right? So you just differentiate that the area is fixed, and you get integral of omega dot is 0. So omega dot has omega dot is anything, but it has to have a average 0. And now let's plug it back in the formula for lambda dot, right? So lambda dot equals this. If you plug everything back in, it means that the numerator has to be 0, right? So if you're looking at the critical points, right? So we want derivative equals 0. It means that this is 0 for any omega dot satisfying this condition, right? And if you think about it, right, you can always take f squared to be the average of omega. If you take f squared to be the average of omega, you'll get something positive unless, sorry, what do I say? Yeah, so I want to say that we can always take the f squared could be anything. All right, so which means not f squared. Apologize. So let me start this argument all over, right? So here in this formula, this equals 0, omega dot could be anything as long as it has average 0. From this, it's easy to see that f squared has to be orthogonal to all those omega dots, right? So, but the only thing which is orthogonal to omega dot is a constant function, right? Otherwise, omega dot could be anything. Therefore, f squared has to be a constant function, right? But thus, f squared was an eigenfunction, right? So something doesn't quite add up, right? So something is wrong here in this argument. And if you want to, so I propose to you, if you'd like, you can pause the video and try to think about what's wrong with this argument, right? Which is somehow, again, it's a fundamental feature. And what's wrong with this argument is not some technical stuff that I'm burying, right? So I'm telling you that this argument is technically correct, right? So there's something more, something a little bit deeper, what is wrong with this argument, right? So you can pause the video, think about it, and now I'm going to give you the answer of what is wrong with this argument. The wrong thing is actually this, right? If you want your functional to be, if you want your metric to be extremal, this is not the right condition. And then let me tell you why. Let's look at this example, right? So G extremal does not imply that the derivative of the eigenvalue itself is 0. Let's look at this matrix. The matrix looks like this, right? So it's just T minus T. So the eigenvalues of this matrix look like this, right? So around 0, this is just two rays. You see that it is critical at 0, right? So this is lambda 1. The graph of lambda 1 is red, and the graph of lambda 2 is blue, right? So because the eigenvalues might have multiplicity, you can still differentiate them, but when you differentiate them, they switch places, right? So at this point, after this point, lambda 2 becomes lambda 1, and lambda 1 becomes lambda 2. So essentially, this is not the right condition of extremality, right? So the right condition is something else. So here's an example where you have a critical point, right? So you clearly have that lambda 1 is maximum along this deformation, but derivative is not 0. right? So the right condition here, and it's precisely because you could have multiplicity at the extremal metric. And as we noticed before, the condition that we obtain actually requires multiplicity, right? So the sum of squares equals constant requires multiplicity. And we already see from here, right? So if there's no multiplicity, then you have a nonsense, right? So you have to have multiplicity to not have nonsense like this. Right, so what actually happens in general? Right, so in general, the following happens. You have your eigenvalue, lambda k, but it is multiple. When you do deformation, each this eigenvalue splits, right? So it has several branches and they split off. And it splits off like this. And so what happens is that the actual computation that we just did, it works for the slopes of those branches, right? So for branches that split off, if the slopes exactly computed like we just did. Right, and then your condition becomes is actually those slopes. The slope on the left is positive, right? And the slope on the right is negative, right? There has to be one slope which is positive, and it has to be at least one slope which is negative, right? And this is a condition of extremality. So mathematically, it is expressed like this. So G extremal for lambda k, if this matrix is sign indefinite, right? So where Fi is in the corresponding eigenspace, Ek. Right, so what happens is that the eigenvalues of this matrix exactly control the slopes, right? So eigenvalues of that matrix, they equal to the slopes of those branches of eigenvalues, right? So you have to have one non-negative slope and one non-positive slope in order for it to be extremal, right? And that's why I'm calling it sign indefinite, right? So it's neither positive definite nor negative definite, right? So if it's positive definite, for example, then the picture would be like this. So if this A is bigger than 0, your picture looks like this, right? So all slopes are positive. So the last one is kind of too much, right? So it's like this. So the first eigenvalue in here is this, and it's not critical, right? But if at least one of them goes down, then it suddenly becomes critical, becomes extremal. Right, so that's kind of that's the main point here is that if you have multiplicity of eigenvalues, instead of in that computation, instead of the actual derivatives, you get derivative of different branches, and then you have a just condition of the eigenvalues of this matrix, in condition that's sign indefinite. And actually, the same picture implies the opposite condition, right? So if you know that this lambda k is the first in this cluster of eigenvalues, and the converse is true as well. Right, so if you're looking, so let me maybe elaborate on this point a little bit. So if you're actually looking at the first eigenvalue, at this eigenvalue in this cluster, then this is enough, right? The fact that A is sign indefinite is enough to guarantee extremality. But you could be looking, if lambda k minus 1 equals to lambda k, then you could have been looking at this one, and then it's not just sign indefiniteness of A itself is not enough, right? So you need to have 2 positive and 2 negative eigenvalues, right? So this is if G is extremal, then A is sign indefinite. If additionally the previous eigenvalue is strictly less, then the converse is true, right? If A is sign indefinite, then lambda k, G is extremal for lambda k. Okay, good. So hopefully I convinced you that this is the right condition, right? So we now need to investigate when does this matrix is sign indefinite, right? So this is a matrix defined. This is a bilinear form defined on the eigenspace, right? And we know that this form is nothing but the integral of omega dot FE/FG. Right, and so the proposition is that this actually happens. This is sign indefinite if and only if, sign indefinite for all perturbation, if and only if there exists collection of functions whose squares sum up to 1. right? I'm going to give you the proof in one direction, so you kind of just see that why is this the condition, right? So if you have the collection such as sum of squares is 1, let's see that that's good enough for us, right? So by contradiction, suppose it is sign definite. For example, it's positive, right? So it's positive definite. Then you just have this easy computation, right? So you have for each UI, you know that a UI is positive, right? But a is just the right. So this dot UI, as we discussed, this is just the omega dot UI squared. All right. So if you look at this, then that's what you get, right? So 0 is bigger than this, and if you sum up over all i's, you get UI squared equal 1. So you get just the average of omega dot, but we just discussed that the average of omega dot is 0. And you get a contradiction, 0 is less than 0. Great. So this is one direction. Other direction is it's a bit harder, right? So to prove that if it's sign indefinite, then you have this sum squared equals 1. This is kind of akin to like sub-differential conditions, right? So this is something that occurs when people study these objects which are not quite differentiable, right? So the eigenvalue, the branches of eigenvalues are differentiable, right? But if you order them, then you can have this angles that we've seen before, right? So, and this is techniques. There are some techniques which are used in study of such objects, and the one of them is Rand-Banach separation theorem, right? So if you have two convex sets, you can separate it by a plane, and that's how you do it. I don't want to go into details of this. I'll give you the reference. So the reference is a survey paper by Fraser and Shane. It's minimal surfaces and eigenvalue problems. I should tell you that they go into detail of both Steklov eigenvalues and the usual Laplacian eigenvalues that we're considering, right? And they explain in detail how they are connected to harmonic maps and minimal surfaces. They mainly talk about minimal surfaces, so it's something we're going to talk about now, but a little bit later, not now, but a little bit later. But there's also some parts about this, right? But the argument is very close in both cases. Okay. All right, so we proved this theorem of Najashvili and El-Sufi. El-Sufi is that you have this extremality condition with sum of squares equals 1. Right, so now, as I promised, now let's explain why this condition is equivalent to being harmonic map. All right, so let me recall what it means to be harmonic. So the map to Sn is harmonic if it's critical for this energy functional. Right, so this is so here g phi. So this squared, you just have g phi as a vector of differentials, right? So it's du1, du2, etc. You just take sum of squares of all of them, right? So it's nothing complicated. Just a vector function. So you have this. So it's critical of its energy function. And one observation is that it only depends on the conformal class. So this energy only depends on the conformal class of the metric G. If you change the conformal class, it's something I mentioned last time when we talked about measures. This integral does not change. So if you consider respect to H, which is in the same conformal class, then this term gains some factor, but dvg also gains the same factor with power -1. So they cancel out, and Eg is the same. So it only depends on the conformal class. So property of being harmonic only depends on the conformal class of metric G. It doesn't depend on the particular choice of the metric in the class. So let's find the equation of this harmonic map for particular case of maps to a sphere, right? So the same type of argument, right? Consider deformation of phi t to some different map to a sphere and take derivative, right? So when you take derivative, you just take derivative and you get this, right? So in here you move this d to the left-hand side, d becomes delta, and delta d is a Laplacian. So you get this. Right now, what is the condition on phi dot? Right, so phi dot cannot be just anything. You have to, your condition is that phi t squared has to be 1, right? So it's always a map to sphere. And when you differentiate this, take a dot of this, you get that phi dot is 0, right? So phi dot is always orthogonal to phi. So looking at this, you get that, and it's the only condition of phi dot. So it means that Laplacian of phi should always be parallel to phi, right? So it's true for any phi dot which is orthogonal to phi, which means that the Laplacian phi is parallel to phi. You can actually find the coefficient exactly, and you do it just by computing Laplacian of this phi squared, right? So phi squared is 1 because it's mapped to sphere. Compute Laplacian of it. Laplacian of the product enjoys this property. So the point that the minus here is because my Laplacian has a minus sign in front, right? So compared to the usual second derivative, sum of second derivative, which has a plus. For that Laplacian, you'll get plus here, but for this positive Laplacian, you'll have a minus. And it tells you that the product of Laplacian phi with phi is always d phi squared, no matter what. And so the end result is that phi is harmonic is the same as that phi satisfies this property, this equation. And it's the same as phi, Laplacian phi being parallel to phi. Right, so this is how you, so you can just think that map is harmonic if and only if it satisfies this equation. And now we can establish this correspondence, right, between extremal metrics and harmonic maps. So let me explain the one direction, right? So suppose we have a lambda k extremal map. Lambda k extremal, sorry. Suppose we have H in the conformal class of G, which is extremal for normalized eigenvalue, for kth normalized eigenvalue. Right, so which in particular extremal in this conformal class. So we're only allowing perturbation in this conformal class. So what happens then? Right, so as we just established, there exists this map, and this map has Laplacian phi equals lambda k phi. So it's a map by eigenfunctions whose sum of squares is equals 1 to it. So it's a map to a sphere by eigenfunction. And you see that lambda k phi is parallel to phi. So which means that this phi is a harmonic map. And there you go. Right, so phi is a harmonic map to Sn by the lambda k eigenfunctions. Right, so this is correspondence in one direction. Somehow remarkably, you have the opposite correspondence. For any harmonic map, you can find an extremal metric generated by this. It might not necessarily be a maximal metric, right? So it will not be maximizer in the space in the whole conformal class, but it will be critical point, right? It will be satisfying this derivative zero condition. So what do you do? So suppose we have a harmonic map. So harmonic map means it satisfies this equation, right? And here is there another place where conformal covariance comes into play, right? We can change the metric G so that phi become eigenfunctions in that metric. Components of phi become the eigenfunction, right? So we define a new conformal metric G phi by this formula. And then by conformal invariance, this equation transforms into this equation. So in metric G phi, right? So we just take this to the left-hand side, divide by it, and then hide it in the metric. So by conformal, so this is a map by eigenfunctions. All right, so which means that phi is a harmonic map to Sn by lambda k eigenfunctions for some k, right? So it tells you that those phi are eigenfunctions, and they correspond to some lambda k. And this lambda k is multiple, right? Because you have many components of phi. So the smallest such k, we have lambda k equals lambda k plus 1, et cetera, right? So the smallest such k will be called the spectral index of phi, or in the S of phi. And so what we get, and note that for smallest such k, you have that lambda k minus 1 is strictly less. Right, and if this property of being strictly less is sufficient to go the other way in the correspondence, right? To assume to go from having indefinite metrics to having an extremal metric. right? So which means that this metric G phi is extremal for the eigenvalue with this index. So this is very remarkable in the sense that you have those, you have bijective correspondence essentially, almost bijective, right, between extremal metrics and harmonic map. If you start with extremal metric, you get the harmonic map immediately. If you start from harmonic map, you could pick a metric in the conformal class, which will be an extremal metric generated by this map. All right, so let me give some final remarks on this. So this partially explains conical singularities, which we've seen last time. Right, so what happens is that the harmonic maps, they might have points where G phi is 0, which means that this metric G phi will have zeros in the conformal class, right? But those zeros, it turns out that those zeros of G phi are isolated for any harmonic map, and they exactly correspond to the conical singularities. And moreover, you can compute the value of this, of the corresponding metric. And it turns out it's exactly, so it's this, right? So we know that eigenvalue is 2. You can compute the integral, right? So it's just dvg times this over 2, and then 2 in front cancels out. And it's exactly twice the energy, right? So the value of the function that we have here is exactly the value of the energy. Right? Again, very natural correspondence. And so this is it. And I want to finish with explaining how extremal metrics in the space of all metrics correspond to minimal immersions. Right? This will take significantly less time because I'm going to skip the main step. Right? So so this step is still the same, right? So if you have extremal metric in the space of all metrics, then the matrix, the same matrix, is sign indefinite for all variations. So the main difference here now, if we allow deformation in any direction, not just in the conformal direction, is that this expression is much more complicated. Right? Computing the derivative of Laplacian is more complicated. So I just want to do it here. Again, you can go back to that reference of Fraser and Shane, where we do it in a great detail. But essentially, if you follow the argument, again, use this Hahn-Banach separation type argument, what you end up having is that, so of course, you'll have this collection of functions such as sum of squares equals 1, right? If you're extremal in the space of all metrics, you're extremal in the conformal class, of course. But you'll have an additional condition that the sum of sort of the induced metric, right? So the left-hand side here, this is just the induced metric. This is just phi g of induced metric from Sn. This metric is proportional to the original metric for some constant alpha. Right? In particular, so this is the additional condition that you get, right? So our goal now is to show that this implies that this map is minimal. So in particular, this map phi is a conformal harmonic map. Right, so by conformal, exactly. By conformal, I mean that the pullback of the metric is in the same conformal class as G. All right, so conformal here just means that the pullback of the metric from the sphere is in the same conformal class. Right, so my goal now is to explain to you why conformal harmonic maps is the same thing as the minimal immersions. Right, so let me remind you what does it mean to be minimal immersion. Right, so if you have two Riemannian manifolds, I will not define it intrinsically, I will define it via the map. Right, so oftentimes minimal manifolds define just intrinsically. I want to attach a map to it because basically that's how they appear in this context. So the immersion of M to N is called minimal isometric if it's extremal for the volume function, all right? So we can pull back the metric from manifold N, compute the volume in this metric, and say we want to be critical. All right, and so we have this isometric coordinate here, and the pullback of the metric is the metric that we started from. So in our case, if M is a surface, we will use notation area of phi instead of the volume of phi. So this is general definition for any dimensions. We're going to use the A of phi because we have area instead of the volume. And so let's look at the relation between area functional and the energy functional. It's actually very fascinating. So how does area relate to energy? So suppose we have a local orthonormal basis of mg. So what is the integrand of the area, right? So what we do, so we want to compute the, we take a pullback metric, right? So the pullback metric will have these entries in this basis, right? So we'll have the derivative with respect to phi, derivative with respect to Eg, phi. And you will take square root of the determinant. We'll have this form, right? So this is E1 with index on top is the dual form. It shouldn't be D, right? So that's what I. So D shouldn't be here, right? So it's just E1 wedge E2 without the D. It's going to disappear on the next slide, but D is not needed, right? So E1 and E2 is just a dual one forms, dual basis on one forms. And the integrand of the energy, right? So this is this, right? So du1 phi squared plus du2 phi squared. And so let's in the same form. So let's compare those two, right? So what is the comparison? We have the same matrix A, right? Whose entries is those scalar products, and we're looking at the trace. So this is the half of the trace, and this is square root of the determinant. So I claim that there's always an equality like this. Trace B is bigger than twice the determinant of B for any 2x2 symmetric B. So let's see why. So if we take B, the matrix B, it has the terms A, B, C, C. All right, so what is the trace B? Trace B is A plus B. We're claiming it's bigger or equal than twice AB minus C squared. Right, so if we take a square, we have A squared plus 2AB plus B squared bigger or equal than 4AB minus C squared. So you move the 4AB to the left-hand side to get A minus B squared bigger or equal than minus C squared. All right, so on the left-hand side, we have a positive number, and on the right-hand side, we have a negative number. So the usual thing. The one thing that I want to emphasize here is that you have equality here. Equality if and only if A equals B, so the left-hand side is 0, and C equals 0, and the right-hand side is 0, and it's rearranged terms. Right, and this exactly means that phi is conformal. Right, so you'll have that your metric, the pullback metric, is A times the identity matrix corresponding to the fact that E1, E2 is in a orthonormal basis. All right, so the takeaway from this computation is that the energy is always bigger or equal on A of phi. Right? That's actually why we put 1/2 in front of the energy, precisely so that it agrees with area if phi is conformal. Right, so you have this energy bigger or equal on area with equality if and only if those two equalities are satisfied, and it's the same as saying that this map phi is conformal. Right, and so let's now use this to show my previous claim. So if you start from a minimal immersion, then you get, it's always a harmonic map. Right, so you have this branched minimal isometric immersion, then it's a harmonic map, period. In opposite direction, if you have a harmonic map, which is also conformal, then if you take the induced metric or metric G phi, this is a branched minimal immersion, right? So let's prove this. So my first thing is that I want to, so our G phi, what it was G phi, let's recall. It was half of the G phi squared G, right? So this half is put here precisely so that this is true, right? So we put half so that this agrees with the pullback metric if phi is conformal. Okay, so phi is conformal if and only if this is true. And now this proof is actually very elementary, right? So what you do, you write energy in this form, right? And now suppose that we are in the setting of the first one, right? Suppose we are critical for the area. It means that derivative of this is 0. But at the same time, branched minimal immersion, right? We know the pullback metric coincides with the original metric. So it's automatically conformal, which means that it's actually 0 of this quantity G minus A. But G minus A is always bigger or equal than 0. So if it's equal to 0, it means it's local minimum, global minimum even. Therefore, derivative is 0. Right? So for conformal maps, derivative of this term is 0. For minimal immersion, derivative of this term is 0. Therefore, the derivative of this term is 0. Conversely, if we have a harmonic and conformal, all right, so for conformal map, derivative of this term is 0. For harmonic map, derivative of this term is 0. Therefore, derivative of this term is 0, and we have a branched minimal immersion. Right, so there you go. So this is how this is proved. So the takeaway here is that the harmonic maps are conformal harmonic maps, essentially the same as the minimal immersions, right? So let me just address this word branched, which is everywhere in brackets, right? So branched just means that you have to allow your pullback metrics in here when I talk about immersions, right? So my phi, when I talk about harmonic maps, my phi could have zeros, right? Zeros of d phi. When I pull back the metric, I don't quite get an honest metric. I might get a metric with conical singularities, right? And in this case, people add the word branched in quotations. They also oftentimes call such maps not conformal, but weakly conformal to emphasize that they could be zeros of the conformal factor. But those are technicalities. I don't want to go into it too much. Right. So what did we learn today in this video? So harmonic maps to ascend correspond to extremal metrics in a fixed conformal class. Branched minimal immersion to ascend correspond to extremal metrics in the space of all metrics. Right. So this is what was sort of the cornerstone of the second video. Right. Something we used throughout the second video. And this is the key part, right? So for surfaces, harmonic plus conformal is the same as a branched minimal. And if you're curious about this branching properties and you were annoyed by the fact that I didn't talk about it too much, so this is the reference where it's explained very well. Right? So in this reference, the branching and conical singularities are explained in the context of this eigenvalue problem, right? So how to work with it, how does branched minimal surfaces differ from, how do they differ from the usual minimal surfaces? And finally, next lecture, we'll talk about harmonic particular case of M being S2 and RP2, and we'll talk about the modular space of harmonic maps from S2 and RP2 to Sn, and this will use a lot of complex algebraic geometry, complex analysis, like Riemann surface kind of stuff. This will result in twistor correspondence. All right, thank you. Hopefully see you in the next video.